Hello everyone, I'm back with section 15.2, which is color and electromagnetic spectrum. This is not new section for you guys. In one or the other way you learned this and very similar thing in chemistry, so it will be a kind of review for you guys. So a wave on a string, if you guys remember what we have seen, if you have a string and if you wave the string, a wave on a string causes a string to oscillate back and forth, and a sound wave causes air molecules to oscillate back and forth. The question is, what oscillates back and forth in a light wave? So light wave consists of oscillating electromagnetic fields. There is a field, or that just like a soccer field, there is an electromagnetic field, as shown in a figure below. So note that the electric and magnetic field are perpendicular to one another. As you see at the bottom of it, there is a magnetic field and electric field, and these two fields are perpendicular to another. So this is the direction of the motion of light. So as the light travels away from the source, it has two different fields, the magnetic field and the electric field, which are perpendicular to one another. So these are the thing that propagates. It is not like air. It is not air like sound. It is not the part of the string like the wave in a string. Light waves are just one example of a large group of waves known as electromagnetic waves. Electromagnetic waves that our eye can detect is known as visible light. Electromagnetic waves produced in nature when an electron in an atom oscillates back and forth. This sends out an electromagnetic wave, just like shaking one end of a string sends out a wave. Electromagnetic waves can also be produced by oscillating electric currents. When electric current oscillates, it also produces electromagnetic waves, not only electrons. Even shaking a bar magnet produces electromagnetic. Let's say if you have a magnet like this, which is a straight magnet, if you shake it, probably around, especially a coil wire, it produces electromagnetic waves. The frequency of electromagnetic waves is a key to its behavior. For example, different colors of visible light, those rainbow colors, are produced by electromagnetic waves of different frequencies, but light isn't the only type of electromagnetic wave. Visible light corresponds to only a small portion of a visible light, or it is only a small portion of a possible frequencies. The full range of frequencies of electromagnetic waves is known as electromagnetic spectrum. So a wave has all types, whether it is light or other forms of wave, they do have a speed, frequency, and wavelength. A wave speed and frequency and wavelengths are related by the equation speed equals to frequency times wavelength. All electromagnetic waves in a vacuum have the same speed, c, which is 3 times 10 to the power of 8 meters per second. And therefore, the frequency f of a wavelength lambda of electromagnetic waves are related to the speed of light. C is equals to f times lambda. Regardless of the difference between them, all electromagnetic waves have the same speed as that of light, which is approximately 300 million meters per second. A wave speed, frequency, and wavelengths are related by the equation speed equals to frequency times lambda, which is wavelength. All electromagnetic waves in a vacuum have the same speed, which is c. Therefore, the frequency f and the wavelength lambda of an electromagnetic wave are related as c equals to f times lambda, which is frequency times lambda. The product of an electromagnetic wave's frequency and the wavelengths must be equals to c. This is if the frequency of an electromagnetic wave increases, it is wavelengths decreases. So frequency and lambda or wavelengths are inversely proportional, but their product is constant C. This diagram shows you all types of electromagnetic waves or ranges of frequencies based on their range of frequency. As you see, the radio wave has the lowest frequency, and microwave follows radio waves, and infrared and visible light between infrared and ultraviolet followed by X-ray, which means higher frequency than ultraviolet, and gamma ray. But when it comes to the wavelength, as you see, gamma ray has the highest frequency, 10 to the power of 20 to 22, but where radio wave have even much more lower than 10 to the power of 8. It goes around 10 to the power of 7 and 6. But in terms of wavelengths, the radio wave has a longer wavelength, which is about 1 meter. But as you go from radio wave, in terms of wavelengths, radio wave is longer than microwave is longer than infrared has a longer wavelength than visible light has a longer wavelength than ultraviolet, and ultraviolet has a longer wavelength than X-ray has a longer wavelength than gamma, which means it has the shortest wavelengths but the highest frequency, the longest wavelengths at this end, and the lowest frequency. So let's see each of these one by one. Radio wave. This is a wave with the lowest frequency and with a practical importance of the frequency range is between 1 million to 1 billion hertz. These are the waves that are used in both radio and television broadcasting. In addition to molecules and accelerated electrons in space, give off radio waves, and the radio astronomers can detect these waves with the large dish receivers like the one shown in the picture. So this one will detect a radio wave. So a radio wave is a wave at which the radio and the televisions are all broadcasters. And the other wave is a microwave. A microwave is electromagnetic radiation with the frequency from 1 billion to 1 trillion. Okay, from 10 to the power of 9 to 10 to the power of 12 hertz. These are referred to as a microwave. A wave in this frequency range are versatile. They can be used to cook food in your microwave oven, and they can carry your telephone calls by cell phones and through Wi-Fi connections, or maybe to the internet. So this is the area where the internet and the cell phone, when you call with a wireless, they use a microwave, from cooking to your cell phone. Infrared waves are electromagnetic waves with frequencies just below the red light, roughly from 10 to the power of 12 to 10 to the power of 14 hertz. These are known as infrared or IR waves. These waves can be felt as heat on our skin, but we cannot see with our eyes. For example, sometimes when you sit on a chair and when you stand up from that chair, if you touch it, you don't see that heat, but you can feel on your skin. Sometimes when you touch, maybe something, and you don't see these waves, but when you touch it, you feel it in the form of heat. That is what is known as infrared hits or infrared waves. So animals like snake, frogs, some fish like goldfish and salmon, and some insects which depends on human blood, for example bed bugs and mosquitoes, they do have infrared receptors, which means they can see infrared radiation, so which means the light that comes from your body, and then they can come towards you to suck your blood or to hunt other animals. Visible light. This is a spectrum of visible light. As you see on the right side of the figure, you see the rainbow. A full range of colors, which we see in a rainbow, is a part of a visible light because we can see it. Each different colors in the figure produced by electromagnetic waves in its own frequency. And the other one is ultraviolet light. When electromagnetic waves have frequencies just above that of violet light, from 7.5 to 7.5 times 10 to the power of 14 to 10 to the power of 17 hertz, And when it lies in this range, it is known as ultraviolet or UV rays. Although these UV rays are invisible, they often make their presence known by causing sunstain. UV lights are also given off by galaxies in the region of stars formation, as shown on the right figure. Sometimes you go to the beach and you feel burned, sunburned. That is because of UV lights. X-ray is another form of electromagnetic spectrum. These are radiations in the range of electromagnetic spectrum between 10 to the power of 17 to 10 to the power of 20. These are energetic rays, and they can pass through our bodies rather freely, except when they encounter bones, teeth, and other relatively dense material. An X-ray image of the hand is shown in the figure below. So the X-ray, you can see the bones, but it can't penetrate the bones, but it can penetrate the fleshy or the meat or the body, other body. X-ray can cause damage to human tissue, and it is desirable to reduce unnecessary exposure to these rays as much as possible. You have to have a protective shield when you go to X-ray rooms. And the last one is the gamma rays. These are electromagnetic waves with frequencies above 10 to the power of 20, and it goes to 10 to the power of 22 hertz, is referred to as gamma rays. Gamma rays are highly energetic and can be destructive to living cells. It is for this reason that they can be used to kill cancer cells, which is known as chemotherapy. More recently, microorganisms in the food also can be killed by gamma rays. Human eyes has three types of light-sensitive cells that detects red, green, and blue light, respectively. Because of this, the colors red, green, and blue are known as primary colors. What colors? Red, green, and blue. These three colors, remember, the primary colors, red, green, and blue. All of the colors we see in nature, from red to orange, to yellow, to green, to blue, are produced in our eyes by different amount of primary colors. What are these primary colors? Red, green, and blue. So the specific way that the primary colors combine to form other colors is illustrated in the figure that you see here. So if you mix, you see, outside, you see there is a red, green, and blue. Outside, that the outside rings are the primary colors. When you mix red and green, you can find yellow in equal proportion. When you mix red color with blue, you form magenta. And when you mix blue with green, you obtain cyan. But if you mix blue, green, and red, all of them in equal proportion, you will find white color. Red, green, and blue are known as additive primary colors, since these colors add together to produce white light. Combining two or more of these primary colors results in either yellow, magenta, cyan, and white. Manufacturers of television and the computer screen take advantage of the additive primaries. Each picture element on the pixel on a TV screen consists of three dots or three color dots, as shown in the figure. Red color dot, green color dot, and blue color dots. Lightning combination of colors dots and varying the brightness allows the screen to display any desired color. The figure below shows you that the pixel looks like as it produces various colors. Note that red and green color dots are lit to produce yellow. You mix them together, it produces yellow. And red and blue produces magenta. Red and blue produces magenta. If you bring red with blue, it produces magenta. And blue and green produces cyan. Lightening all these dots in a pixel produces white. If all of them are shined together, it produces white. Lightening none of them produces black. None of them. If there is nothing of them, the color will be black. So make sure that you see that's red only. Here is two of them producing yellow, and these two producing the color behind. Green by itself, blue by itself, blue and green producing cyan, and blue, all of them mix it together producing white, and missing none of them will be, all of them, missing all of them will be black. Not all colors are produced by the source of lights, like the color dots on a TV screen. Sometimes colors is produced by subtracting or removing some of the colors in a white light. This is done with pigments, the paint that we use for our home, like those used in paints and dyes. Yellow paint or pigments looks yellow because it absorbs blue light and reflects red and green, and the mixture of red and green is yellow. That is what comes to our eyes, that is what we see. So the combination of the two light that is reflected, which is red and green, produces yellow. Similarly, a cyan pigment absorbs red light and reflects green and blue. A magenta pigment absorbs green light and reflects red and blue light. Cyan, magenta, and yellow are known as subtractive primary colors. These are the colors that can combine to produce any desired colors by subtracting light. If all three subtractive primary colors are combined, they subtract all colors from light, leaving black, mixing all the three, yellow, magenta, and cyan. If you mix all of them, it will finally turn into black. But these two produces this, these two produces this, these two produces this, because this is a color that is combined between these two. This is a color which is a combination of these two, and this is a color of the combination of these two. So that's all about section 2. On the next section, we will see about the polarization and scattering of lights, and probably we might skip that section, but I'll let you guys know. And thank you so much, and then go to your homework and do your homework now.